Hi everyone. How are you guys? You don't sound like you're good. You sound a bit bored. Okay, I hope I won't bore you anymore. So my name is Kathleen Siminyu. I am a data scientist at Africa's Talking. I also run a community for Nairobi women in machine learning and data science, although we are open to all, so you should feel free to check us out sometime. And the topic for today, my session, actually my lecture, let's call it a lecture. My lecture today is called Unblackboxing Neural Networks. I know the program says demystifying, but I felt that making up a word of my own would be more appropriate. So unblackboxing neural networks. And the method of understanding neural networks that I'm going to be discussing is network dissection. So before we jump into all those deep things, I'm going to start with the pre-introduction to the introduction. So let's start very basic, in case you've never heard of even artificial intelligence. Basically, it is the development of computer systems to be able to perform tasks that normally require human intelligence. So making a decision or translation or looking at all of you guys and saying this is a man, that is a woman, those are all things which as humans we just do, but computers have to go through some training to be able to do the same. So machine learning is a field under artificial intelligence, and basically it entails giving systems the ability to learn and improve from experience without explicitly programming them. So there's different ways that you can give machines this intelligence, and one of them is machine learning. So you feed them loads of data rather than coding many if-else statements to say if hair is short, man, if hair is long, woman, then you just give it loads and loads of pictures and let it learn how to tell the difference. So machine learning. And then now within machine learning, there's a field called deep learning, which is the field within which my lecture is on. So basically deep learning is a way of teaching machines by imitating the human brain in processing data and uncovering patterns. So they really just model the human brain in terms of there's neurons, and the neurons are in layers, and then there's edges connecting layers, and then data or information is being gleaned from neuron to neuron, from layer to layer, and the machine is learning interpretations. So we'll see how it goes from low-level interpretations, and then it puts this many things together and collates them and then makes a decision, okay? So I could be looking at one person and looking at what they're wearing, maybe I look at their shoe size, maybe I look at whether they have facial hair or not, but at the end of it all this is put together, and then my machine decides, yes, this is a man or this is a woman or whatever. So yeah, I've basically just explained what a neural network is, and it's a function at the end of the day. It's a mathematical function. It takes in inputs, does some calculations, and then gives you an output that is supposed to solve a particular problem that you have outlined. It comes in layers. I'm sure you've heard of neural networks having many layers, but this is the most basic structure, where you have an input layer, an output layer, and then the hidden layer is in the middle. The layer in the middle is called the hidden layer. So when you hear people talking about deep networks, basically they have very many hidden layers in between the inputs and the outputs. And the way a neural network is trained, please let me know if I'm going too fast, although I may not be able to do anything because I'm on a bit of a time limit. But okay, so the way neural networks are trained is hidden layers activate on certain things. Like I've mentioned, when a machine is trying to decide, okay, let's just run with this man-woman example. When a machine is trying to decide, is this a man, is this a woman, it would hypothetically look at different factors, yeah? So these are all factors which each neuron will learn, or rather, each neuron learns a certain factor, okay? So if there's a neuron which, for example, learns your shoe size. There's a neuron which learns the length of your hair. There's a neuron which learns the clothing that you're wearing. And then at the end of the day, all that they've learned is collated into what is a fully connected layer, and then we get an output, which is just a probability distribution in the case of a classification. So yeah, this happens over and over again. Every time you feed it an input, the weights are adjusted. The weights are at each neuron, and that is what directs our learning. So the weights are what are going to make each neuron adjust to whether it is learning well or not. Let me just go back to, a computer doesn't really know what it's learning. You're the one who's teaching it. And the way a teacher would mark your tests and tell you this is right, this is wrong, a neural network has to have a function which is directing it in a certain direction, so that it knows this is more of what you should be doing and this is more of what you should not be doing. So the weights and biases are what are going to be changed as we are training. Our training process is us changing these weights and biases and taking them towards what reduces our cost function, or whatever function it is we're using to train our network. So forward propagation is one of the ways that neural networks are trained. You just basically feed in data, and then an output is given. Then you compare the output with what the truth is, and then the difference from where the truth is and what you predicted is your cost function. So that's how you'd learn. Okay, so I've said all of this. Output of forward propagation is compared to the output of what is known to be correct, and the cost is the difference between the two. That is the point of training, to make the cost as small as possible. And like I said, to do this, the neural network tweaks weight and biases step by step until the prediction closely matches the correct output. And then once trained, we can make pretty accurate predictions. So the method network dissection, which is the method of beginning to understand neural networks that I'm going to be talking about, is based on convolutional neural networks. I like convnets mostly because from a human standpoint, you can sort of intuitively see what your network is learning, as opposed to if you're just, I don't know, analyzing like the stock market, and it's just numbers. Anyway, so the intuitiveness that comes of being able to see an image and then comparing that with what the net gives you, so that you can see, in this neuron it was learning this, and in this neuron it was learning that. So convolutional neural networks, they're widely used for computer vision, and they have three main layers. There's very many different architectures of convolutional convnets that we're going to look at, but they have three main layers, so just keep in mind these layers. There's the convolutional layer, which is a filter. Think of it as a sort of filter that is scanning this whole room, and each filter, okay, my net is no longer there, but each neuron would be a filter, for example. So if I'm the neuron that's supposed to detect shoe size, I'm scanning this whole room looking for shoe sizes. So when I detect a shoe size, I remember it, yeah? So yeah, that's the convolutional layer. Then there's the rectified linear unit layer. That's our activation layer. It makes the decision, basically. After each convolutional layer, yeah, you see, after each convolutional layer, a lot of times there'll be a ReLU to just make a decision. So in the case of, again, the neuron that's looking for shoe size, it's going to be scanning, and then maybe it's going to activate highly on your shoe size. It's deciding, yes, this is a shoe, as opposed to a cat or a dog or someone's hair. So that's the activation layer, and then there's the max pooling layer. So there's a lot of things this network could learn, and a lot of it could be noise, or some of it could be noise. So rather than trying to dig through all the noise, we're just going to maximize on whatever activates highest, yeah? So if a layer learns that there's, I don't know if there's what. If the layer learns that there's a dog, and then behind the dog there's a chair, and then underneath the chair there's maybe some dust, the dust is like almost meaningless. So we'll just maximize on the fact that there's a dog. Yeah, I hope you understand, but that's basically what the max pooling layer does. Dimensionality reduction. It ensures that the network focuses on the most relevant patterns. So neurons in a given filter share the same weight and bias parameters. This is for convolutional nets. Other nets have different architectures, but just keep that in mind for convolutional nets. And this is what allows the filter to look for the same pattern in different parts of the image. Like I said, it would just go scanning, looking for what it wants to identify. And they are trained using backpropagation. So remember how earlier I talked generally about neural nets being trained using forward propagation? Okay. I should ask someone what forward propagation is. But yeah, so convolutional nets are trained using backpropagation, which is basically just, let me use this diagram to explain. You'd feed in your input at the start, and then forward propagation is the input coming in, all the weights and biases being calculated, and then the final fully connected layer giving you a decision after the activation. So for forward propagation, that's where it ends for each training step. You get your output, you compare it to how far you are from the ground truth, and then you have your loss. But then with back propagation, you take the loss and then you do another run going back, so that all the weights and biases are adjusted based on how much closer, or based on reducing the cost function. Remember how I said the cost function is what tells the net whether it's learning in a desirable direction or not? So we want to make the cost function, or rather the loss function, as small as possible, so that we know it's learning as much as possible. So yeah, basically the backward pass is just updating all the weights and biases with what we have learned in the forward pass. Cool? Oh guys, feedback. Kwanza, all you Africa's talking people, why are you here if you're not cheering me on? Anyway, okay, so so yeah, this is what a convnet looks like. Like I said, the 3 layers constitutes convnets, but there's very many different architectures. So you could even sit down and write one of your own, man. You could just decide, I want this number of convnets, this number of fully connected layers, etc. But basically, each conv layer is followed by an activation layer, so that your decision is made, and then you pile them up. And at the end of the day, we get a probability distribution. So remember how I was trying to explain how, rather than trying to understand everything, we just take what gave us the most signal. So in this case, the convnet identified a car, or rather it gave more weight to there being a car than, for example, there being a horse in whatever image it was viewing. So onto the many architectures of convolutional nets that are out there. If you follow deep learning, I'm sure you've heard of some of this, like the AlexNet. Okay, so I wish I'd gotten the context of like years that they've won the ImageNet challenge and stuff like that, because these are pretty famous architectures. But let's just concentrate on the number of layers that they have, because that's going to be important when we come to dissecting the models and seeing how well they perform. So the AlexNet has 5 conv layers. The VGG, which is another very famous one, has 16 convolutional layers. The GoogleNet has 22 convolutional layers, and then the ResNet has over 100 convolutional layers. So yeah, man, things really get deep sometimes. Thank you, Bob. See, feedback, guys. So the 3-layer combinations, in whatever architectural way someone has decided works best, could discover many complex patterns. Some of these complex patterns could make sense to you, they may not. They could make sense to the net, they may not. They may be noise. So trying to understand what the network is learning is the point of this session. Enter network dissection, which is the method I'm going to be discussing today. So it's carried out on the basis that each neuron is a concept detector. So each neuron learns one thing. And if you remember the layers, a layer could have like 256 neurons. And then of those 256 neurons, each is either learning something or not, basically. So we're trying to figure out if they're identifying anything meaningful. And once we get the activation level, which is a number. Just think of all this as numbers, guys, because it's all just math. So once we get the level of activation, a feature map is used to sort of paste this on whatever picture you're looking at, so that you can begin to get a sense of what the neural net is looking at, or what it is learning. So basically, the framework identifies hidden units semantics for any given CNN and aligns them with human interpretable concepts. We're taking the weights and we're taking the activation levels, or whatever outputs the net is giving us, and putting that onto an image in this case, and seeing if it has actually learned something meaningful. So this is an AlexNet, and we've dissected it now. We're looking at the 5th convolution, at the 5th conv layer, and at the various units in it. So for example, it was given input. This is a pre-trained model. Yeah, I should probably mention that. So you'd pre-train a model, okay. So this AlexNet in particular is taken and pre-trained, and what that means is you give it a data set. So the particular data set that it's been trained on has takes into consideration different things. So there's a data set in there that is going to be focused on texture, another one that's focused on color, another one that's focused on, say, images, another one that's focused on scenes. So your net is learning what a classroom looks like, what a bathroom looks like, what a kitchen looks like, what the texture of wood might look like or feel like, and stuff like that. So it activates on various things that it has learned over time. So this is a model that's already been trained, and then I pass through a picture. And in this picture, there happens to be a lamp, or there happens to be lamps in whatever picture or data set I'm passing through it. So we see that in convolutional layer number 5, unit number 1 is activating on lamps. So because of the light, you may not be seeing, but eventually you'll get these slides. So these are basically all just lamps. And number 2 is activating on cars, but it's not completely foolproof because some of these are bird heads, which if you really think about it, bird heads probably have the same low-level representations as a car, because if you think about it, they have like gleamy eyes, and cars have headlights, and yeah, yes?
It's a quick question. Like, the neural nets, the hidden layers can get pretty large, like maybe you have like 16, 17 of them. How do you know that that's like the most efficient, or can it go like lower, fewer layers?
Well, it depends on your problem set, but again, it just comes from training and iterating. Because as a data scientist, I feel like your work is just trying to find the best model, and sometimes that could just be you creating a search grid and saying, search these parameters. So search this number of layers, search 10, 20, 30, and then you just compare how it performs on your particular problem set, and you optimize it to the best. So how deep does it go? How big are the layers? What activation functions do you use? I know I've mentioned ReLU, but there's quite a few activation functions out there. What regularization functions are you using? There's also quite a few of those. It's called hyperparameter tuning, actually. It's a whole topic on its own. But yeah, finding a model is pretty interesting. So this is an AlexNet. It's going to be the baseline of the graphs that I show you today, and it's been trained on a data set of places. So it's been, yeah, like I said, it's going to be able to identify living rooms, kitchens, the coast, the beach, the desk in the classroom, etc. And so it's pre-trained, and then it's been trained on places, and I put a data set through it. And this histogram at the bottom is basically telling me what unique detectors were found in conv layer number 5, which has 256 units. So 256 units is 256 neurons, and that's 256 different things each individual neuron could be learning. But they're not always learning sensible things, meaningful things. They could be learning noise, but then also they could be learning concepts which you have not trained your model on. Remember how I talked about this model being pre-trained, and it's pre-trained on data sets that give it a certain span of knowledge. So it can identify colors, can identify textures, it can identify straight lines, shapes, objects. So if you wanted to identify something which you've not trained it on, or rather if a unit identifies something which you have not trained your model on, it's going to be characterized as noise, yeah? Because these are all things your net is doing. You're not actually investigating all 256 units to see their outputs. You're just being given a score. So if you're going to be if a neuron is going to be identifying something which you've not trained it on, it's going to get a low score, even if that thing is meaningful. So again, how you pre-train your model is pretty important. So back to the histogram of object detectors. So like I said, conv layer number 5, 256 units. But of the 256 units, there were only 40 unique detectors. That means 256 minus 40, all the rest got pretty low scores, so we discarded them. And okay, actually there were 81 things detected, but then of those detectors, only 40 were distinct. So this histogram is just showing you what was most detected. So like water got the highest, followed by grass, tree, etc. And you can just look at all 40 particular categories. And now this is what a dissection report would look like, yeah? So this is the histogram of object detectors which we've gotten from that AlexNet baseline model. And then there's a couple of other things which you can look at. So there's scene detectors. Has it, how many ball pits, what, I don't know, like a ballpark? I don't know what a ball pit is. But skyscrapers, mountains, snowy, auditorium, these are all things which the net has detected and annotated. And then there could be parts detectors, so hair, wheel, crosswalk, head, back pillow. And then texture detectors, so banded, lined, studded, dotted, etc. Oh, I realize now that it would be easier to just read from here. But yeah. So this stacked bar chart basically just summarizes everything in this dissection report. You can see over here, can you see my mouse hovering? No? Okay. So at the bottom is blue, and blue is the object detectors. So we can see that the AlexNet has recognized, like in comparison with the rest, we can see how many objects, how much texture, etc. So yeah, and then putting it as one bar enables us to be able to compare it with different architectures. So looking at the bottom, this is AlexNet trained on Places and AlexNet trained on ImageNet. Places was our baseline model, so this is the one we've just dissected. But then, you know how, okay, I don't know if you know this, but basically in deep learning, the deeper you go, the better the results are supposed to be. This is not always true. Sometimes a simpler model is what you need. Like you don't need to go that deep if you don't have so many features. But if you have a very big data set, the deeper the model, ideally, the more it will learn. So this is just us just analyzing how much different network architectures have learned. So AlexNet trained on Places 365 was our baseline. We can see that the VGG, for example, which has 16 layers as opposed to AlexNet's 5, ranks better than its pre-trained on ImageNet as well as pre-trained on Places 365. It's learning more. And then if you remember looking at that, what's it called? The thing that tells you what's going on, the legend, yeah? You can see how much object detection it did, how much color detection it did, for example, how much texture detection, etc., etc. So also please note that going lower, when you have less layers, it detects less objects. And this is because, if you remember, each layer learns a representation and then it passes it on to the next layer, yeah? So the network is not going to wake up today and identify a whole human. It's going to start by scanning and identifying, oh, this is hair, oh, this is a nail, etc. And then it's going to pass this information to subsequent layers, which will now start to identify bigger things. So like this is a face, or this is a hand. And then by the end of the network, we see this is a person, which is why architectures which have less layers, you find that their object detection is not so great. But with the low-level stuff, they have pretty significant numbers. So like texture, material, you can see these ones are pretty big over here. In some cases, even bigger than the object detection. But then when you get now to the really deep architectures, they are like through the roof. For example, ImageNet, not ImageNet, ResNet, which has over 100 layers. And then trained on this Places dataset, it blows through everything. It learns almost everything theoretically. So yeah, the deeper you go, ideally the more your network is learning. And yeah. So now we're going to look at a couple of comparisons of the different networks picture-wise. So this is an AlexNet neuron that has identified a house. I don't know if you can see clearly, but it's just pointing out the roof, yeah? Then this is on VGG and GoogleNet. It's now identifying whole houses, and then in ResNet, it's identifying pretty complex complexy looking houses, yeah? Something like if you give an AlexNet a castle, it might look at it and think, oh, that's a triangle at the top, because that's its level of understanding. But by the time you've gotten to over 100 layers, a ResNet can make pretty sophisticated discernments. And then this IOU is basically just the score that's telling you with how much certainty your net is identifying these objects. So the AlexNets, you can see the score is increasing with the deeper the network is. So 0.05, 0.07, and then we get to 0.13, 0.142. So the ResNet performs better because it's deeper. We expect that. Then also we can do an airplane example. This is a neuron that's identifying airplanes. Again, on the AlexNet, it's just identifying certain parts. So it can see like the wing or the thing at the top, whose name I don't know. And then the VGG now is identifying almost a whole plane. And Google Net again is getting better. Watch the scores as well. They're also getting higher. And then by the time we get to the ResNet, you can't see this, but then in this particular image, there's a guy standing in front of the airplane. So with a lot of machine learning models, a little noise totally confuses them. You could show it you could show it a data set with like 5 million planes, and then you test it with one image which has a guy standing in front of a plane, and it's going to go completely haywire. But then a ResNet is pretty sophisticated. I mean, it's identifying images which have occlusion. You could like flip or rotate your image and it would still identify the image, as opposed to lower units. I mean, less layered networks. Oh, so that's actually my last slide. But I wanted to show you guys a couple of demos of different ways that this network dissection can also be used. So network dissection can also help you with your training process to just see where your network converges, or if it has converged at all, as opposed to just relying on your loss function. So this first video is showing our training process, and we've identified one unit to see what it's learning. And we can see at the beginning it's learning the color red. Like I said, it starts with really low level representation, so color, texture, material, etc. So it's learned red, and then it learns road, then it learns blue, and then it finally rises and converges to learn a car. Yeah? And I don't know if you can see, but as the video is playing, the images on the side actually move. So that you can see at each step, this is what it's identifying in an image until it's finally seeing a whole car. So this is pretty intuitive. It's a pretty intuitive way to train your network also, to just see when to stop training, when it starts overfitting, for example. And then it can also be used with transfer learning. So transfer learning is it's a concept where you take a model that has been trained on a particular data set or particular problem area, and then you try and fine-tune it to another problem set. For example, I'm just going to give an example from work, from something I've been learning about. So, mass data set, which has it was compiled by Google, I think. It has millions of images of almost everything in the world. So he takes a network that's trained on ImageNet, and he tries to, I think he tunes it to the places. Anyway, I don't know what he tunes it to, but he takes a trained image and then he tunes it to some other context, and this is how the neuron changes what it has learned. So it starts having identified a dog. We see it goes to tree, it goes to white, and then it finally stops at waterfall. And the way you can intuitively think about this is, if you look at the pictures of the dog at the beginning, the dog is it's black and white. Think of the low-level concepts that the network learns at the beginning. It learns color, it learns material, etc. So this dog in this particular case is black and white. And then as the video progresses, at the end we see that the way it's outlining the waterfall, which it finally learns, it pretty much looks black and white. So we can infer that it's just learning low-level concepts and collating them and then giving you an output, which now to you makes sense. So yeah, that's somewhere else where network dissection can be used. This is the end of my presentation. Does anyone have any questions? Yep.
Hi.
I have two questions.
Uh-huh.
One is the machine learning libraries like TensorFlow.
Uh-huh.
So is it easier to, let's say, use TensorFlow or to write and design your own neural network? Then the second question is, in your examples you use mostly supervised learning. So is deep learning only useful for supervised learning, or can it also be used for unsupervised learning?
Okay, so deep learning is actually better for unsupervised learning. If I go back to the slide where we're comparing different architectures, there's actually a few nets over there which are trained on unsupervised learning. So from this point onwards, it was supervised learning, but then again, I guess I should have mentioned with unsupervised learning in this instance, it performs less. It performs less better. It doesn't perform as well, yeah, which is why I didn't dwell on it so much. But there are problem spaces where deep learning is excellent, and especially for unsupervised learning, because it can learn so many concepts, especially, okay, so here we're sort of putting together what the net has learned with what is human interpretable, yeah? But in very many problem spaces, all you need is the numbers. You need to know what is the variance, what is the mean, etc. But all those numbers are not necessarily always human interpretable. So it is actually really good for certain contexts, just not in this case. And then your first question was what?
Let's say using TensorFlow versus designing and writing.
Well, all those libraries are just tools for you to, at the end of the day, write your own networks. So in some cases, it's easier to just get an already trained network, which is why guys will take the AlexNet or the Google Net or the VGG and just fine-tune it to their own problem space. But you could just take TensorFlow and write your own net from scratch. It's actually tools like those that make it very easy to do stuff like that. So they're not like mutually exclusive. Yeah, that is exactly what TensorFlow is for. Yeah. Have I answered your question?
Kind of. I was concerned about, as in, is it easier to use TensorFlow versus doing it from scratch by yourself? Or
in plain Python? Well, with optimizing, if you're going to be using a lot of data, then the optimizations that TensorFlow gives you would be major wins in terms of compute and also just the time that it takes, because TensorFlow abstracts all of that in their tensors, or even Caffe or PyTorch. I don't know why we're dwelling on TensorFlow. I hear that it's a bit clunky compared to some other.
Stating it as an example.
Okay, okay, cool. Any other questions? Okay, I hope you all enjoyed the session. I slaved preparing it, which I'm really glad I did. Now that I see the recording, I'm just like, yes. So thank you guys. Thanks for listening.